So when we started talking about energy, we said energy is the ability to do something, the ability to do some stuff, right? And it turns out that work is that stuff. Energy has units of joules, which is a Newton meter, right? And that means that it is the amount of energy it takes to apply 1 Newton of force for a distance of 1 meter. And work is the connection to that force and distance. Work is equal to force times displacement. More specifically, it's the dot product, but we don't need to worry about that. So work is equal to force times displacement, right? And that produces a change in energy, right? If I push against a box that was at rest, it started with no energy, and then I give it energy. So it turns out that work is also equal to the change in kinetic energy. Lastly, work is also equal to the negative change in potential energy, right? If you think about dropping a ball, if I drop a marker or I throw something into the air, when kinetic energy goes up, potential goes down. When potential goes up, kinetic goes down. So these are opposites. So using work, we are able to account for situations where energy leaves a system or is put into a system. For example, me pushing a box is putting energy into the system. A box sliding over a surface with friction is energy leaving the system. So let's look at a framework of how we approach those problems. So our first step, 1, is to identify the initial energy. I'll just write ID. Identify our initial energy. And because work is interested only in a change in kinetic or a change in potential, you're either going to have Ki or Ui. Step 2 is to ID your final energy. And because, again, it only cares about one energy at a time, you're going to have either Kf or Uf. Step 3 is to calculate the work. So you have to calculate the work being done, which you're going to do in terms of force times distance. And here, you really need to watch the sign. You need to be careful. Work is positive if the force of being applied to the object and the motion of the object are in the same direction. Okay? If they're in opposite directions, then work is negative. Another way to think about it is, at least for kinetic energy, if you put energy into a system, you're going to increase its energy, so work will be positive. And if energy leaves the system, then the work's going to be negative. So then the last step is to use our second definition of work, which is that it's equal to the change in kinetic energy or the negative change in potential energy. And here we're going to say, okay, well, work is equal to delta K, or if you're doing it in terms of potential, then work is equal to negative delta U, and then we substitute. So then, okay, work is force times displacement. So we have F dot D equals your final kinetic minus your initial kinetic. Or, if you're using potential, you're going to have force times displacement is equal to your initial potential minus your final potential. So notice that this is Ui minus Uf. The reason for that is because the negative sign, so we take the negative of final minus initial, which is initial minus final. So using this 4-step method, you should be able to solve pretty much any work problem that comes your way. So let's look at an example. Let's say I have a box of mass m, and let's say I push it with a force of F, and I push it for a distance of d. Let's say it starts at rest, so v naught equals 0, and I want to find the final speed after it moves that displacement d. Okay? So let's go through our steps. So our initial energy, EI, is equal to 0. Because what's changing here is its kinetic energy, right? So it has final kinetic energy, but no initial kinetic energy. So Ki is 0. Our final energy is kinetic, so it's going to be 1/2 mv squared. And our work is force times distance. The force being applied is F, and our displacement is d. So it's going to be equal to F dot d. So now we can go ahead and solve this. We say, okay, well, work is equal to our change in kinetic energy, right? So work is force times displacement equals change in kinetic. So our final kinetic energy is 1/2 mv squared minus our initial is 0, which means that FD equals 1/2 mv squared. So solving for V, we're going to multiply by 2, divide by m, take the square root, and you get that V is equal to the square root of 2FD over m. And remember that this work is positive because the force and the displacement are in the same direction. Okay? Let's do another example. Let's do one with friction. So let's suppose that a block of mass m is traveling with a velocity of v naught, and it's traveling over a surface with friction. I'll say this surface has a coefficient of friction of mu k, and let's say that the distance over which the friction exists is d. And again, I want to note the final speed, Vf, of the object. So our initial energy is going to be kinetic, so I'll say Ki is equal to 1/2 m. It starts with the speed of v naught, so 1/2 m v naught squared. Our final kinetic energy is going to be 1/2 m Vf squared. And then the work done, which is W, is force times distance. And in this case, our force is friction. So we have mu k mg times the displacement over which it acts, which is d, and that's our work. However, the force of friction is in the opposite direction, right? Additionally, energy is leaving this system. It's going to slow down. It's going to lose kinetic energy. So this is a negative. So from here, we say, okay, work is equal to our change in kinetic energy. So negative mu k mgd is equal to kf minus ki, with kf being, I'll just write those down, kf is 1/2 m Vf squared minus ki is 1/2 m v naught squared. So solving for Vf, we're going to have, we can cancel out the m's. We can multiply by 2 across, and we'll add this to both sides. So we're going to have Vf squared is equal to v naught squared minus 2 mu k mgd. Oh, we got rid of the m, sorry. So mu k gd. Now if we want to solve for Vf, we'll take the square root of both sides, and we're done.